Chapter 17, Advanced Disease Risk Statistics. This chapter is really only for those people who are interested. It's not necessary to know this kind of information for using genetic information. It will give you a deeper understanding of how to estimate genetic risks based on a number of different genetic variations. But really, the simple disease risk statistics are enough to understand the program. And in case you really are interested, here is a deeper look into the statistical calculations of genetics. So, first, please watch the simple disease risk statistics to be able to understand this part, because this is an additive part. I will not explain the simple things again. All right, so as I explained in the other training, you have three different possibilities for a genetic variation. Wild type, both genes have a G, odds ratio of 1. Heterozygous or homozygous mutant. Now the question is, how do we find out what genetic risk a homozygous mutant has compared to the wild type? And in this case, scientists perform case control studies. And they start with a hypothesis. The hypothesis is this gene variant increases the risk of diabetes. So step one is to identify subjects. And it would be very good to have a large number. So you use 1,000 diabetics and 1,000 healthy people, for example. Next step is perform gene analysis and count the number of genotypes. This is what it would look like. You draw this kind of table. You check diabetics, do a genetic test for all of them, and you find out half of them, 500, have the AA genotype, so the mutant, and 500 of them are wild type. And then you do the same on the 1,000 healthy people, and you might find 100 have the homozygous mutant and 900 have the healthy type. So once you have this table, you can do the calculation to find out the odds ratio. And this is how you do it. You calculate the diabetics mutant, these 500, times healthy wild type, these here, divided by healthy mutant times diabetics wild type. And then you get the odds ratio. So if you put in the numbers, you will get an odds ratio of 9. So as I've explained in the other training, what does this mean? The scientifically absolutely correct meaning is, if a person has diabetes, the likelihood that this person has the AA genotype, the bad genotype, is 9 times higher than that this person has the AA, the good genotype. So this is a bit difficult to understand. So what doctors usually do, as well as scientists, they simplify it and they say a person with the AA genotype, the bad genotype, has a 9 times higher risk of developing the disease. Now this is quite correct. It's not absolutely correct. The calculation is a bit more complicated. It doesn't really mean it's 9 times higher. But this is a simplification to understand odds ratios. It's very close to the statistical truth. So for the purpose of using genetics, you can really say an odds ratio of 9 means you have a 9 times higher risk of developing the disease. But keep in mind, it's slightly different. It's not 100% exact. So now we have odds ratio of 1 for wild type, odds ratio of 9 for homozygous mutant. 9 times higher risk of diabetes than a person with GG. Now next question, heterozygous, what's the risk? You do the same kind of calculation again. You look at the diabetics, how many are heterozygous, how many are wild type, healthy, how many are heterozygous, how many are wild type. Put in the numbers and you get an odds ratio of 1.55. And here's the number. So this person has a 1.55-fold risk compared to the wild type, and this genetic type has a 9-fold risk. So odds ratio of 1 is a 1-fold risk compared, and odds ratios are always compared to something. That's important to understand. So this is a 1-fold risk compared to the other genetic types. This is a 1.55 risk compared to the optimal genetic type. This is a 9-fold risk compared to the optimal genetic type. Now, very simple to do for an individual gene. One gene has a variation, higher risk, you have a higher risk. However, there are also polygenic disorders, which means lots of genes influence the development, and diabetes is such an example. There are a number of genetic variations, 7 in this example, that can increase the risk of developing the disease. Some laboratories offer one, so you can really look at this one gene, you say, yeah, I have a higher risk. However, this is an incomplete picture. You really need to use all of the genetic variations that you know. Hopefully you get all of them. There are still some in science that are going to be discovered later, but usually the worst ones or the most important ones are easier to detect and already known. And then you do a genetic test and some studies, and then you find out, for example here, that PPAR gamma, the wild type has an odds ratio of 1, the heterozygous 1.19, and the mutant is 1.28. So these are the 3 different genetic results you could have in this gene. And TCF7, 1 for wild type, 1.65 for heterozygous, and 2.77. So different numbers that we got from scientific studies. Now you can do a genetic test, and then you find out the person has the wild type for this gene, odds ratio of 1. Heterozygous for TCF7, homozygous for this gene, and so on. Now you have a number of odds ratios. Now the question is, which one applies? And this is what you do. You multiply the odds ratios with each other. So you do 1 times 1.65 times 4 times 1.34 and so on. And then in the end, you get a total odds ratio of 35.13. So a person that has this genetic type has a 35 times higher risk of developing diabetes than a person with the optimal genetic type, which is here. Some people would assume, why are you multiplying this? Why not add them together? Because it's increased risk by all of them. Multiplying would make the risk a lot higher. Why not add them together? And actually here you see why. Because if you look at the optimal genetic type, that must be an odds ratio of 1. Because here you would suddenly get a 1, 2, 3, 4, 5, 6, 7. If you would add it, you would get 1 plus 1 plus 1 plus 1 equals 7. So really the optimal genetic type would already have an odds ratio of 7, which obviously is incorrect. But if you multiply it by the multiplicative model, you get 1 times 1 times 1 times 1 times 1 equals 1. So really statistically and mathematically correct, you need to multiply the different risks by each other. And the optimal genetic result is going to have an odds ratio of 1, and the highest is going to be a multiplication of the highest risks. I have to say, this is the multiplicative model, and it applies to most diseases. And this is the standard model that scientists use to determine the overall risk. However, in some cases, scientific studies have shown that the additive model is correct. So in some cases, that's what we do when we know about the science. We add the risks together, and in other cases, we multiply them. And this is really the stuff of scientists or the role of scientists to do the science, to find out how they combine. And the known information is combined in these programs. So comparing the 2 different examples, the optimal type and the random increased mutation type, means that an example, a person with this red genetic type has a 30 times higher risk of developing diabetes than a person with the optimal genetic profile. So this is how you work with multiple odds ratios. Now, a genetic variation has a number of identifiers because many scientists work with the same genetic variation, and they all need to know what they're talking about, but they are talking about the same thing. So from a genetic variation, we find out the gene where the variation is located. This is the name of the gene. The name of the variation, the RS number, it's kind of like a catalog number for a genetic variation. This is a unique number, and every scientist that looks at it knows, it's this genetic variation they're talking about. Then you have the different bases, the different genetic letters that can be at this variation. And then we can also find out the frequency of these genetic variations, which means how common each of these gene combinations are in the general population. And there's a website here in case you want to play around with it a bit. It's the NCBI website. And there you can enter this RS number, and then you get this list here. And here, for example, in the European population, you get these bars here. And what does this mean? You have AA, AG, and GG. That's the 3 possible results for this genetic variation. And here you can see AA, it's most of the bar. So AA means 70% of the European population have an AA at this position. 27% have an AG, and 1.8% have a GG. So this in Europe is how common this genetic variation is. And in Asia, it's fewer people with AA, some with AG, and more with GG. So there's really, there is a difference between different populations. In most cases, it is how common this genetic risk is. The genetic variation still usually causes the same disease risk. It's just less likely that a person might have it. But this is the kind of information that we can get from here. So now we know AA 70%, and we know it's the wild type, so we have an odds ratio of 1. AG is 27%, we have an odds ratio of 2.5. And GG is a 1.8% of the population, have an odds ratio of 4. Then we can calculate what is the average genetic risk in Europe, because the general population, usually when you analyze many genes, most of the people have some genetic variations. So if you do the calculation, this is how you do it: 70 times odds ratio of 1, 27 times odds ratio of 2.5, and 1.8 times 4 divided by 100 is an average odds ratio of 1.45. So based on this gene, the average risk that the general population has is 1.45. Some will be a higher risk, some will be a lower risk, but the average is 1.45. So if you draw a risk scale, if you have an odds ratio of 1, you would be here, 2.5 in the middle, and 4 you would be here. And we know that the average population is at this position. So you can either say the odds ratio is 1 for the optimal genetic risk and the rest is relative to the optimal genetic risk. However, we also know that if you're on the right here, compared to the general population, you have a higher risk. And if you're on the left, compared to the general population, you have a lower risk. So an odds ratio of 1 is actually lower than that of everybody else. An odds ratio of 2.5 is higher than that of everybody else, because you just look at the average compared. So if we look at an odds ratio of 9, means there's a 9-fold risk of disease. The disease risk is 9 times higher. It's all the same meaning, it's just different ways of saying it. You can choose whichever one you like best. The risk of disease is increased by 800%, but be careful, it doesn't mean you are 800% likely to develop the disease, which would obviously be incorrect. The relative risk of disease is 900%. 900% times the risk of disease, not a 900% likelihood of developing it. Be very careful with this information. And this is actually my favorite. Comparing subjects from group A with an odds ratio of 9, so if you have people with an odds ratio of 9, and you compare them with people who have an odds ratio of 1, and you have 1,000 people in each of them, this group is going to have 9 times more cases of developing the disease than this group. So this is what an odds ratio means. And this information, odds ratio, is always relative compared to something. So this group has a 9 times higher risk of disease compared to the group with the other genes. Yeah? So looking at this odds ratio means compared to the optimal genetic profile, this person has a 2.5 times higher risk. So relative to the optimal genetic variation. However, there's another way of displaying this. And this is saying the general population has an odds ratio of 1. Everybody together has an odds ratio of 1. Compared to everybody else, as we know, the people with the optimal genetic profile have a lower risk. So actually what you get is an odds ratio of lower than 1, so it's 0.8. And this would then be an odds ratio of 3.5. So sometimes you will see odds ratio of 1, it might mean the optimal genetic profile. Sometimes you see odds ratio of 1, it might mean the general population. And usually when you see an odds ratio for a genetic result that is lower than 1, that means they took the general population as the standard where everything else is calculated relative to. So you can have a genetic result that gives you an odds ratio of lower than 1. And this is how you calculate with protective lower than 1 odds ratios. It's the same thing. You do the genetic test and see here this person had a protective genetic variation. Again, multiplying it, you get an odds ratio of 0.95. So compared to the general population, this person has a 5% lower chance of developing the disease. It might also be severely higher or even lower. Now, how do you calculate the probability of developing a disease? I've already explained the problem with calculating disease probability. It's really the aim to reduce the probability of developing the disease in terms of preventive genetic testing. It's not the aim to tell you 80% likelihood you get this disease. Sorry, that's a diagnostic test. But let's look at breast cancer, how you can estimate it. I have to say this is a statistical estimation. It will not be exact, but it will give you a rough calculation, a rough expectancy of how many people you would expect would develop the disease. Now for breast cancer, there are 10 gene variations that are involved. Many people have a few of these gene variations, and the population average is an odds ratio of 10.83. As I've said, many of these genetic variations are so common that the general population tends to have a combination of these. And the general population has an odds ratio of 10.83. We also know that from genetics, the lifetime risk of women for breast cancer is 12.5. That means 1 in 8 women develops breast cancer. So, irrespective of the general population, we know that the lifetime risk of the general population is 12.5% for breast cancer. Now, the odds ratio relative to the optimal genetic profile, when you look at the population average, it's an odds ratio of 10.83. Then we take a woman, she has a lot of genetic variations, and her odds ratio is much higher, so it's 30. So the general population has 10, and the woman has 30 compared to the optimal genes. But as I said, hardly any people have the optimal genes. The general population has some genetic variations. So now you can do a conversion. What is the odds ratio relative to the population? That's the next question. So this is the calculation that you would do. 1 times 30 divided by 10.83. And then you get an odds ratio compared to the general population, which used to have an odds ratio of 10, of 2.7. So now the general population has an odds ratio of 1, and relative to them, this person, who used to have an odds ratio of 30, has an odds ratio of 2.77 now, because you just look at a different relative position. So the average population has an odds ratio of 1 through this conversion. The example odds ratio for a woman is 2.77. And now let's look at what does this mean for disease likelihood. Her risk is 277% of that of the general population. Her risk compared to the general population is increased by 177. It's the same thing, just different words used. And it is 2.77 times more likely for her to suffer from breast cancer. Now, if you want to calculate or estimate, it's an estimate you need to consider, you want to estimate the likelihood of her developing breast cancer, you look at the average value for women, 12.5%. That's an odds ratio of 1, 12.5% of probability for an odds ratio of 1. And if you look at 2.77, It's a bit more complicated. This is the calculation you would do, and then her risk is not 12.5 but 30.91. So around a 31% probability of developing the disease compared to a person who has a 12% chance. So this is how you would calculate it, but as I said, I don't like disease probability calculations in diseases that have preventive potential, because through prevention you can reduce this risk again. So really this is just a calculation, statistical estimation of what it means, but really the aim is to modify this percentage that we've calculated here, and not to communicate this percentage to scare people, because in many cases, and that's what we focus on in our preventive genetic test, in many cases there are things you can do to reduce your risk significantly. All right, now let's look a bit deeper into the calculation of what it means to have a certain odds ratio. If you have an odds ratio of 1 and you know that 20% of the population develop the disease, so you have a group of people, 20% get the disease. If you have an odds ratio of 3, now the question is, what is the likelihood of developing the disease? It's not really 20 times 3, which you might calculate, which would be 60. This is not correct, because if you do the calculation, let's say you have an odds ratio of 10, and you would do 20% times 10, then you would have a 200% likelihood of developing disease. There you can see the calculation would be incorrect. The real way of how this calculation is done is like this. So an odds ratio of 1 is a 20% risk of developing the disease. An odds ratio of 3 means 3 times that, but this is how you calculate it. You get the first odds ratio applied and 20% get the disease. Then a certain number are left. Then you apply it again, that's the second odds ratio. And then some people are left, and then again you apply an odds ratio. So you applied the odds ratio 3 times in succession, and then you get a certain number of people who manage to get through all 3 of these selection cycles. And then you see that there are 49% that did not develop the disease. So there's a 51% probability of developing the disease when you have an odds ratio of 3, while the population risk is 20%. So it's not as easy as multiplying likelihood of disease with the odds ratio. It's a bit more complicated. And as I said, it's not a good idea to communicate likelihood of disease if there are preventive measures who modify this. So this is the background, and if we look at the genetic result of a diabetes test, here we have a number of odds ratios. Some are protective, some are increased risk. We do all of these calculations for you. We don't communicate the likelihood of disease progression. This is not a good thing to communicate. We just show it in a very simple way. You see a bar. Here's the average risk, which is the average population. You might be at a lower risk with protection, or at an increased risk compared to everybody else. So really all of this calculation is done for you. It's a very simple result with the bar, and all of this complicated stuff is already done in the background. And that's the end of chapter number 17. This was Advanced Disease Risk Statistics.